Now we're going to talk about improper integrals, that is, integrals on an unbounded interval, at least for the type 1 improper integrals, which is what we're going to look at in this video. So to start with an example, let's look at the graph of 1 over x squared over the positive reals. So it looks something like that. And we could ask the question, what is the area under the graph of this function, that's a positive function, over the unbounded interval from 1 to infinity? So it is not clear that this question makes sense. In other words, that there is such a thing to talk about as the area under the graph of this interval over an unbounded interval. So this would be this red area where it is understood that this red area goes on and on forever as we move to the right. So on the right hand side, this red area, of course the graph gets closer and closer to the x-axis, but we always have a non-zero strip of this red area going on the right. So can we make sense of that? One way to look at it is to truncate at a certain level, let's say t, and look at the area under the graph from 1 to t. Then it is well defined because we're integrating a positive continuous function on a bounded interval, and we know how to calculate that. So this area here is just the integral from 1 to t of 1 over x squared. Of course, 1 over x squared is just x to the negative 2, so an antiderivative is negative 1 over x. And because the function is continuous and we are on a bounded closed interval, we can use the fundamental theorem of calculus and just take an antiderivative and evaluate between 1 and t. At t we get negative 1 over t, at 1 we get negative 1, so we subtract negative 1. In other words, we get 1 minus 1 over t as the value of this integral, which is also the area, the blue area, under the graph. So now, if there is any way to make sense of the red areas that goes on the right, is if we can just move along that vertical segment at t and move it to the right at infinitum and have something that makes sense. And of course that corresponds to letting t go towards positive infinity in our expression for the integral, giving the value of the blue area. As t goes to infinity, 1 over t goes to 0, and therefore the value of my integral goes to 1. So, symbolically, we're going to write that as the integral from 1 to infinity of dx over x squared equal 1. And here, by definition, the way we've calculated this integral from 1 to infinity is by calculating the integral from 1 to t and take the limit of that as t goes to infinity. And in that case, we can define the area under the graph of 1 over x squared over the interval 1 to infinity to be this improper integral from 1 to infinity, in other words, have the value 1. Now let's play the same game with y equal 1 over x, and we do the same thing. We're looking for the area under the graph of 1 over x over the integral 1 infinity, and we may ask the same question, does it make sense? Can we proceed the same way? So proceeding the same way, we look at just the area from x equal 1 to x equal t, and then we'll see what happens when we let t go to infinity. So when t goes to the right at infinitum. So the blue area here is just the integral from 1 to t of 1 over x. X is continuous on the interval 1 to t, so we can use the fundamental theorem of calculus to calculate this integral. It's just a value of an antiderivative of 1 over x, which in this case would be just ln of x, evaluated between 1 and t, so we get ln of t minus ln of 1, ln of 1 is 0, so we just get ln of t. As t goes to infinity, the limit of the natural log at infinity is infinity, so this goes to infinity. In other words, this time this notion of area under the graph of 1 over x over this unbounded interval does not make sense, because this would be infinite. So in this case, we're still going to denote symbolically the integral from 1 to infinity of dx over x for the limit of the integrals from 1 to t of dx over x as t goes to infinity, but we're going to call that divergent because this limit is not a finite number. So that leads us to the definition of an improper integral of type 1. So let's say if we want to define the integral of a function on an unbounded interval of the form a to positive infinity, we're going to assume that for any t greater than a, the integral from a to t exists, and then we just look at these integrals from a to t, which are well defined, and take the limit as t goes to infinity, and take that as a definition for the improper integral, for the integral on the unbounded interval from a to infinity. Now, of course, this limit on the right hand side may or may not exist, and so when we write symbolically integral from a to infinity of f of x dx, we don't really know in advance whether it's going to make sense or not. If it does make sense, that is, if this limit is a finite number, we're going to say that the integral is convergent. And when it doesn't, in the sense that the limit does not exist, in other words, is infinite, or maybe doesn't exist for another reason, then we're going to say that the integral is divergent. So this formula here is really what defines the integral from a to infinity. Similarly, we can define the integral of a function on another kind of unbounded interval from negative infinity to a finite value b, as long as integral from t to b of the function exists for every t less than b, and then we can look at these integrals from t to b and take the limit as t goes to negative infinity. And similarly, we're going to call such an integral convergent if the limit is finite, in which case the value of this improper integral is the finite limit, and divergent if the limit does not exist. So again, here this formula is what defines this type of improper integral. Again, we don't really know, when we write this improper integral, we don't really know whether it's convergent or divergent in advance, and it really makes sense only when it is convergent. Now, a third type of unbounded interval is the entire line. Can we integrate a function from negative infinity to positive infinity? And fixing a particular finite value a, if the integral from negative infinity to a of f of x dx as defined above in 2 is convergent, and the integral from a to infinity as defined above in 1 is also convergent, then we can define the integral from negative infinity to infinity of the function to be the sum of these two improper integrals, because we know they're convergent. If at least one of these is divergent, then we're going to say that the integral from negative infinity to infinity is also divergent. Now you may say that this is a weird way to define this because it depends on the choice of a. Well, not really, and you can easily make a calculation to convince yourself of that. If we take the integral from negative infinity to b and then integral from b to infinity, and you look at the difference with integral from negative infinity to a and a to infinity, well, you can always say when I integrate from negative infinity to b, it's like integrating from negative infinity to a and then from a to b, and then it's going to cancel out with what happens for the other integral. So it really doesn't matter what value a you take. So here is the formula that we're going to use for improper integrals from negative infinity to positive infinity. Again, if at least one of these two integrals is divergent, then the entire integral is divergent. Now, let's take a look at the case of the integral of 1 over x to the p. We've seen at the very beginning, as motivating examples, the case of the integral from 1 to infinity of 1 over x squared, and we have seen that it was convergent and that the value of the integral was 1. On the other hand, we've seen that when we integrate from 1 to infinity 1 over x, we get something that is divergent. In other words, a limit of the integral of 1 over x from 1 to t as t goes to infinity is infinite, and so we have something divergent. So it depends on the power p. And in fact, we will see that we can establish a simple condition on p for this integral to be convergent. Namely, we already know that when p is 1, the integral is divergent, so we can assume p to not be 1. And that means that here, what we're integrating is x to the negative p, where negative p is not negative 1. In other words, we can use the power rule for integrals. So we look at the definition of the improper integral. It's a limit as t goes to infinity of the integral from 1 to t of this x to the negative p. And on the interval 1t, the function x to the negative p, of course here, as t goes to infinity, we're assuming that t is greater than 1. In particular, 0 is not in the interval 1t, so the function is continuous on the interval. We can use the fundamental theorem of calculus, and an antiderivative of x to the negative p is x to the negative p plus 1 over negative p plus 1. We evaluate that from 1 to t, and we obtain 1 over 1 minus p multiplied by t to the negative p plus 1, which we can write 1 over t to the p minus 1, minus a value at 1, which would be 1. And now you see that if p is less than 1, then t to the 1 minus p is positive, so t to the 1 minus p is a positive power of t. As t goes to infinity, this goes to infinity, and therefore we get an infinite limit and something divergent. On the other hand, is p, if p is greater than 1, then p minus 1 is positive, and so we have 1 over a positive power of t. This positive power of t goes to infinity, so its reciprocal goes to 0. And therefore, you see that in that case, the integral is convergent. So what we have seen is that this integral is going to be convergent exactly if p is greater than 1. If p is less than or equal to 1, it's going to be divergent.